It's 2:30, so let's begin here. So project number 1 is due on Wednesday, Wednesday, February 4th at noon. We will continue in section 1.1. We'll start section 1.2 today. Are there any questions? Okay, so we left off about page 140 of the notes. We just started talking about the fourth and last confidence interval for pi. This is a Clopper-Pearson interval. And simply what the Clopper-Pearson interval is just two quantiles from a beta distribution. One's the alpha divided by 2 quantile, one's the 1 minus alpha divided by 2 quantile. The actual parameters of that beta distribution are a little bit different for the lower bound and the upper bound, but they're quite similar. Now, with this beta distribution, if you remember from last time, I said that these parameters, just in general, A and B, need to be greater than 0. Could it happen that these parameters could actually be equal to 0? Yes. Because, for example, you could observe 0 successes. So, for example, this W could be 0, and that obviously then violates the properties of this beta distribution. So if that were to happen, then what simply is done is for that lower bound, since you can't actually really calculate it, just set the lower bound to 0. And that kind of makes intuitive sense, because if you observe 0 successes, well, it makes sense to have a lower bound for pi to be 0. In a similar manner, you could observe, let's say, all successes, so that W is equal to n. And so then you run into the same problem there, and so that upper bound could actually be set to 1. Okay? If that were to happen. Now, the reason why we talk about this Clopper-Pearson interval is because it has a particular property that none of the other three intervals have. And that is that the true confidence level will always be greater than or equal to the stated level. Always, no matter what. And I might be thinking then, well, why don't we only talk about this interval? Why are we talking about these other 3 intervals too? Well, with that guarantee, though, comes some sacrifice. In terms of your true confidence level might be a lot higher, and especially to get that true confidence level so high, that interval might end up being quite wide. You'll see some examples of that shortly. Now, why don't you want a wide interval? Well, a wide interval, gives you a larger range, you could say, of possible values of pi. And ideally, what you would like to have is as small of a range as possible, while still being at the stated confidence level. So, and in fact, this Brown et al. Paper that we were talking about last time as well says that this interval is actually wastefully conservative and is not a good choice for practical use. I think that's a little bit of an extreme. I don't necessarily agree with that, but that's what they say. So here is then a plot, a true confidence level plot for the Clopper-Pearson interval. So we saw those again last time, where we have values of pi on the x-axis. On the y-axis, we have the true confidence level, and n is equal to 50, alpha is 0.05. So the goal is to be at exactly 0.95. And you can see with these true confidence levels, you're always at least 0.95. Oftentimes, you're way higher. Now, an interval such as the Clopper-Pearson interval is what's called an exact interval. Now, sometimes students confuse what exact actually means, or they're confused by what it means. What is the incorrect meaning of it is that you are exactly at 0.95 for the true confidence level, or 1 minus alpha times 100%. And that's not correct. Instead, where the word exact comes in is the fact that in order to derive the interval, and I know we haven't went through the derivation, it requires some stuff that you would see in Stat 882, which is above this class, so that's why we're not going to go over it here. But in order to derive the exact interval, you actually use directly the binomial distribution rather than do these normal approximations that we had seen from the previous intervals. So that's where the exact comes in. Do you have a question?
Does it mean the 99% confidence interval is not as good as 95% because it's wider?
Well, it depends upon what you mean by good. With a 99% interval, you have a higher level of confidence. In order to get that higher level of confidence, yes, that interval will be wider than a 95% interval. Now, if you think of good as how much confidence you have, well, then the 99% is better. But if you think of good in terms of what your width is, well, then the 95% is better. Okay, does that make sense? Okay. So using, as I kind of said before, using a relationship between the binomial and the beta distribution, that's why you see the beta distribution given in the actual confidence interval limits than seeing the binomial distribution given. It's just some nice mathematical statistics stuff that allows you to see the relationship between the beta and the binomial, and that's how it comes about. If you're a stats student, it doesn't hurt to take a look at your old Castellenberger book and look it up. I think I do give a reference, yes, page 82 of the Castellenberger book. Now, I just want to briefly mention that there is another exact interval that can be used for pi, and that is what's called the Blaker interval that was more recently proposed. And this interval is a little bit less conservative than the Clopper-Pearson, but you're still guaranteed to have at least 1 minus alpha times 100% confidence for your true confidence level. The reason why I don't typically talk about it in this class is because it's a lot more complicated to calculate, but there is actually a function that automatically does it, and I give that function, it's briefly discussed in my book, if you want to investigate it further on your own. So let's take a look at how we can calculate the Clopper-Pearson interval. So I'm going to come back over here to my CIPI.R program. Again, remember we were looking at the example where we had 4 successes out of 10 trials. We're doing 95% confidence interval as well. And down here, I give some code for calculating the lower and upper bound. So the lower bound, again, is just a quantile from the beta distribution. So just like what we saw for the Q norm function, guess what? There's a Q beta function. The probability that we want for that lower bound is alpha divided by 2. The A parameter, R calls it shape 1. That's where you put in your W. And the shape 2 parameter, or what R calls shape 2, what we would call B, is N minus W plus 1. So if you execute that code, you get the lower bound to be 0.12. You can do the same thing for the upper bound as well. Now, if you want to be really fancy, you can actually combine these 2 lines of code into essentially 1 line of code, and that's what I actually did above. You just got to be a little bit careful, and this all works based upon how R does its calculations, based upon vectors of information. So notice here I have a vector that has alpha divided by 2 and 1 minus alpha divided by 2 in it. Then I have another vector here that has W and W plus 1. So W for the lower bound, W plus 1 for the upper bound. And I do a similar thing for that shape 2 parameter as well. Execute that, and we get both the lower and upper bound. Now, also last time I mentioned that there's this package called Binom that does some of these calculations for you automatically. And so if you typed, using the code that we saw before for binom.confident, if you say methods equal all, you will get, oops, I need to actually do library binom first. And if you do binom.confident, you see a line here that says exact, and that's exactly what we got previously for our confidence interval. If you wanted to instead, you could have just simply said, in for methods here, just put the word exact, and you'll just get only the Clopper-Pearson. Well, let's compare these intervals. So on page, I guess 143 and 142, here's all the intervals that we calculated, plus a few more that you don't need to worry about, the Jeffreys and Blaker. And you can see that by far, I think, this walled interval is different from all the rest. I look at that lower bound in comparison to the other intervals. You also see how the Agresti, Kuhl, and Wilson are quite similar as well. This is only with a sample size of 10. And then lastly, with the Clopper-Pearson, you can see how that is definitely wider than the other ones. Or wider at least than the Agresti, Kuhl, and the Wilson. Now, just from looking at these intervals, and let's say someone asks you, well, which one's better? You cannot make that judgment from only looking at the intervals. So you might be saying, well, I like Wilson because it is narrower. Well, yeah, it's narrower, but do you know what the true confidence level is? Well, fortunately, through our little investigations, we understand true confidence levels now. And so now we can make a judgment of, well, which interval is better. Obviously, I would not pick walled. And, and then it comes down to, well, do I want to guarantee that I'm at least 95% confident? If I do, I would pick Clopper-Pearson. If I don't, then I probably would stick with Agresti, Kuhl, or Wilson. Especially since most likely the value of pi that we have is probably not going to be really close to 0 or really close to 1, where we know, for example, the Wilson has some difficulties at times, and also the Agresti, Kuhl can be quite conservative. So that's the logic that you use. In your project, you're going to have to do something very similar. Please, again, don't make your judgment about which one is better based upon simply looking at those numbers there. You have to put in the context of true confidence levels and also expected lengths, or how. Let me back up a second. Sorry, I don't remember off the top of my head right now. Have we talked about expected lengths of intervals? Okay. Let's briefly talk about this. It's not in the notes. Sometimes I talk about it in terms of a project. Other times I don't. I'm going to write this in a little bit more. I guess I don't have to write it like that. I can write it in a more mathematical context. So oftentimes with a confidence interval, you want to know what is the length on average. In other words, what's the expected value of the length? Well, what's the length? It's the upper bound, let's call it U, minus the lower bound, let's call it L. So those are two random variables, U and L, is equal to then the sum from W equals 0 to N of U minus L times N, choose W, pi raised to the W, and I'm running out of room, so I'll go down, times 1 minus pi raised to the N minus W power. So in other words, it's exactly what we have for that true confidence level for, expression, except for instead of having an indicator function in there, we have the length. So in other words, when W is equal to 0, calculate the upper bound, calculate the lower bound. Find the difference. Take it times that probability for the binomial. Then for W equal 1, calculate the upper bound, calculate the lower bound, take the difference, take it times then that binomial probability. Keep on doing that for all values up to N, sum them all up, and that's your expected length. Now, which would you prefer? An interval that had a large expected length or an interval that had small expected length? Based upon our previous discussions, small. But the key is this. You want to also make sure that the interval has a true confidence level that's about around the stated level. So don't think that, oh yeah, I got this really cool interval that I just came up with, and it always has an extremely small expected length. Well, the first thing I would ask you then is, well, what's the true confidence level? If you tell me the true confidence level is, let's say, 50%, when it should be stated at 95%, I say, there's no way I'm going to use that interval. So typically, most people look at first at true confidence level. They want to at least get around 95%. And then after that, they'll look further. Well, which one on average is going to be the shortest in length? That's where the expected length comes in. So based upon our previous discussion, the Clopper-Pearson typically always has a larger expected length than the Wilson and the Agresti-Cool. Actually, I think it's in the homework, if I remember right. That's maybe why I didn't have it in my notes. It's in the homework just as a little thing, additional thing for you to explore. Are there any questions? Okay. Now let's talk about hypothesis tests for pi as well. Now, when there's only one parameter of interest, a simple setting that we're looking at right now, I wouldn't actually do a formal hypothesis test. I just simply look at the confidence interval. And if what I mean by formally do a hypothesis, I'm talking about calculate a test statistic, calculate a p-value. I wouldn't do that. But still, I think it's good for you to know, because especially because others do a hypothesis test. I think it's good for you to know some of the basics of it. And also, this will set you up for success later in this course when we will have to use a hypothesis test to make decisions, and you won't be able to use confidence intervals. So, just to make sure in your first stat class that your instructor talked about this, let's talk about how one would do a hypothesis test with a confidence interval. So let's say that those are my hypotheses there, where pi is 0 is some constant. Maybe we'll just set it to some value just so that we can talk about a numerical value. Suppose it's 0.5. So I want to know, is my, let's say, probability of success maybe on a field goal equal to 0.5? That's my null hypothesis. Or is it not equal? And let's say I go out and take a sample, and I got a confidence interval that looks like this. Okay. Based upon that confidence interval, suppose it's 95% confidence interval, would you reject or not reject HO? You would reject. Because we have shown with 95% confidence that pi is between 0.6 and 0.8. It doesn't get down to 0.5. So therefore, I would say reject. Let's instead say my interval was, let's say, 0.4 is less than, pi is less than 0.5. Would you reject or not reject HO? Not reject. Because it's a possibility that pi could be 0.5. It may not be, but still a possibility. So that's how I would approach it. But if you were to use a test statistic, then we can use this test statistic that we actually talked about last time with respect to the Wilson interval that many of you saw before. This is actually what's called a score test. I won't get into details why it's called a score test, but it's based upon basically the likelihood function that we talked about in a previous class. It's a common way that people do hypothesis tests. And we can see that the farther that pi hat is from pi 0, the larger an the larger an absolute value z will be, right? Okay. And so to make a judgment of, well, how far does pi hat have to be from pi 0 in order for me to reject HO? That's when the critical value comes in. Let's say the 1 minus alpha divided by 2 quantile from a standard normal. So if your absolute value of z is beyond that critical value, then it's like, okay, this z that I'm getting is unusual. I should not have that happen if HO is really true, so I'm going to say HO is false and reject. So that is a score test. Excuse me. And in fact, since that Wilson interval starts with essentially this test statistic and its derivation, if you do a hypothesis test with a Wilson interval or with this test statistic, you'll get always exactly the same results in terms of your reject or don't reject. Because it's based upon the score statistic, some people will call the Wilson interval instead a score interval. Appendix B of my book does go into a little bit more detail about score tests and stuff. Take a look at it if you want to. I'm not going to ask you, about the mathematical details behind those kinds of tests. Now, another way that we can perform a hypothesis test for pi is to do what's called a likelihood ratio test, or LRT for short. We will be using these tests now throughout the rest of the semester. There will only be, I think, one other time this semester we'll talk about a score test, so that's why I don't focus on it. Likelihood ratio tests are very, very commonly used whenever you're doing maximum likelihood estimation and other stuff involving a likelihood function. So in this simple setting, let's talk about what a likelihood ratio test is, and so that when we get to more complicated settings, you'll say, okay, I see the extension. So a likelihood ratio test statistic, or LRT, I'm going to use the Greek letter, uppercase letter, lambda, to help denote it. And all it is a ratio of two likelihood functions. Thus, that's why it's called a likelihood ratio statistic. And this is what the ratio looks like. Let's look at the denominator first. The maximum possible value of your likelihood function such that the parameters satisfy HO or HA. So let's take a look at our HO and HA for this problem. So either pi is equal to pi 0 or it's not. So what's the numerical range for pi? Well, somewhere between 0 and 1. So there's really no restrictions on pi at all. So when do we come up with, when have we seen in the past that maximum possible value of that likelihood function when we didn't have any kind of restrictions at all on pi? Hopefully I didn't put the answer there. At least, well, I'm looking at it right now, I didn't put the answer there. When did we see, when we calculated that?
Maximum likelihood.
Exactly. Remember when we found that maximum likelihood estimate? What we had to do was we tried to make that likelihood function as big as possible, because the bigger it is, the more plausible a particular value of pi that is in that likelihood function, the more plausible that particular value of pi is. So we know how to calculate that denominator already. We've done it in class for that simple field goal kicking problem. Now the numerator is the maximum possible value of the likelihood when the parameters of interest satisfy HO. Again, in this particular setting, this very simple setting, we only have one parameter, pi. And let's say pi is equal, I'm testing pi is equal to 0.5 versus pi does not equal 0.5. So in order to satisfy the null hypothesis, I basically have only one choice. Pi is equal to 0.5. So how do you find the maximum possible value of that likelihood function when HO is true? Well, just simply put pi equal 0.5 in that expression for the likelihood function. That's it. And just simply then take the numerator divided by the denominator, and there's your lambda. Now, a long time ago, someone showed by Mary Wilkes, showed that if you take a little transformation of this lambda, so that log there means natural log, take natural log lambda, multiply that by -2. If you do that, and also you have a large sample, then this transform statistic has approximately a chi-square distribution to it, if HO is true. So just like in your first stat course, when you talk about hypothesis test for a mean, someone showed that this t-test statistic had a t distribution as long as certain things held true, like the null hypothesis was true. Now let's think of some questions, or let's discuss some questions here, so that you can get an intuitive feel for this statistic. Okay. So suppose lambda is close to 0. What does this say about your null hypothesis, do you think? Is it true or is it false?
False.
False. Okay, let's make sure you understand why. Remember, we're looking at, with a likelihood function, you look at what is the most plausible value of pi. The larger the likelihood function, the more plausible it is. And so what we're doing is we're essentially comparing what I got for my maximum likelihood estimate in terms of plausibility to what I hypothesized pi to be. And if that numerator is really small relative to the denominator, that means that this lambda is going to be close to 0. So therefore, you probably say, yeah, I think the null hypothesis is incorrect. Now, on the other hand, suppose that lambda is close to 1. what do you think that says about your null hypothesis? Well, it might be reasonable, because the plausibility of pi that you have for that null hypothesis seems to be rather plausible in comparison to what your maximum likelihood estimate is. That comes directly from your data. So therefore, in that particular case, you might say, well, let's not reject HO, because when I'm hypothesizing pi to be, well, that seems like a reasonable value. I don't know if it's exactly true, but it seems reasonable. Now let's look at it in terms of this transform scale. When using -2 log lambda, well, large or small values, not values, I don't know why I have that in there twice. I want to really emphasize the word value, I guess. Do large or small values indicate HO is false? Now let me walk you through this. Well, maybe you already know what the answer is, but let me walk you through this, because I bet some of you are like, oh, not for sure. So, we said small values of lambda suggest that you have the null hypothesis being false. So let's take the natural log of a small value. Let's say 0.1. Notice that's a negative number. Let's say I get smaller. Now I'm getting, you could say, higher in a negative direction. Okay? Now what happens when I take, so what this is saying is, closer to 0, the more likely that the null hypothesis is false. Now when I take this times -2, what's going to happen? I'm getting larger. So, large values of this -2 log lambda tell us, hey, null hypothesis is incorrect. Small values suggest, well, it might be reasonable. So is this test going to be, let's say, a two-tailed test? Is it going to be a left-tailed test or a right-tailed test, do you think? Right-tailed test, because we're looking at large values on the right-hand side there. And, well, how large is large? That's where that chi-square distribution comes in. Find a 1 minus alpha quantile from a chi-square distribution, and that's going to basically be your critical value, and that's how you make the judgment of reject or don't reject. If it's greater than that critical value, you reject. It's a right-tailed test. Yes? Thank you for asking that. As I was going through that, I was like, I haven't talked about that yet. The degrees of freedom. Actually, the degrees of freedom are fairly easy to find, even though the way I have it worded in the notes, just to be kind of general, is actually might make it more difficult than what it really is. So the degrees of freedom, let's just call it U for the lack of a better letter. The degrees of freedom is the difference in dimension between the alternative and null hypothesis parameter spaces. All that means is this. My alternative hypothesis, how many parameters do I have that are essentially free? Meaning I'm not setting them to particular values. Well, in this case, there's 1. Pi does not equal pi 0. So it's free. It's not set at a particular value. So my parameter space has a dimension of 1 for the alternative hypothesis. For my null hypothesis, I have 1 parameter that I'm setting to a particular value. So I know what it is. So how many parameters do I have free under the null hypothesis? 0. So if I take 1 minus 0, I get 1. My degrees of freedom are 1. That's a very, very general way to find degrees of freedom for a associated hypothesis test. When we get into more complicated problems later, knowing that general way of finding it is going to be a lot more, it's going to be helpful, rather than me just saying, okay, yeah, it's 1. Don't worry about how you found it. Okay? Any other questions? Okay, let's just simply apply.
Sorry.
Yes, sorry.
Can we actually go over that lambda again? I'm not sure I got it.
Okay, so this lambda is a ratio of 2 likelihood functions, and to make sure this is clear, since I'm working with a ratio here, and also just from properties of probability distributions, that lambda is never going to be negative. It's actually going to always be between 0 and 1. Okay, And so the alternative, the denominator then says, okay, let's let h or ha be true. I don't care which one's true. What's the maximum possible value that likelihood function can be? Well, that comes about through plugging in the maximum likelihood estimate into that likelihood function, which we did last week. Then the numerator says, okay, now let's restrict ourselves. Suppose only HO is true. What's the best that I can do in terms of this likelihood function? For this simple hypothesis test here, we constrain our one parameter that we have available to us to be, let's call it 0.5. So all we have to do is plug in 0.5 in there, we calculate it, and then we get our numerical values for our ratio. Does that help?
So we plug in the maximum likelihood function for the null hypothesis, and we
The
divide it
likelihood
by-
function that's maximized, assuming the null hypothesis is true. I think that's a little bit better way to say it. Let's take a look at the example coming up, and maybe that might help too. Okay, so in this field goal kicking example, let's say that pi was equal to 0.5 as a null hypothesis. The alternative is not equal to 0.5. And again, let's say that we have w equal 4, n equal 10. So let's find then the numerator of lambda. Again, since I'm constraining pi to be 0.5, what that says essentially, here's my likelihood function, I just need to plug in 0.5 everywhere you see pi. Do the calculation, and you end up with, also plug in w, plug in n as well. You get 0.0009766. Now for the denominator, we could go back in the notes. I'll just give you a quick page reference. Do I give the page reference there? Nope. The page reference will be page 12 of the notes. And we found what the maximum possible value that likelihood function could be when we don't have any constraints at all, and it ends up being 0.001194. So we just simply plug in those two possible values of our likelihood function, as we do here. We do the math, we get 0.8179. Okay? Do the little transformation, -2 log lambda, and you get 0.40. Now to make a judgment of, well, is that really big enough to reject the null hypothesis? That's where this critical value comes in. The 0.95 critical value from a chi-squared distribution is 3.84. How do you do that? Well, maybe another class you learn to use a table to do that. Well, we're beyond doing that here. You don't need to use tables anymore. We can just go to R and use the Q for quantile, chi-SQ function. Put in your probability, put in your degree of freedom, and you get 3.84. I'm proud to say I haven't used statistical tables in a class for at least 12 years. I don't know why people still use them, to be honest. I mean, we got computers. And they're going to be better because you're not limited to the number of possible values that you can put on a piece of paper. Anyway, so because 0.40 is less than 3.84, don't reject HO. There's not sufficient evidence to indicate that pi is different from 0.5. It may be, but at least from the sample, I don't have sufficient evidence to make that conclusion, that it would be different. Please make sure that's how you word your conclusions for hypothesis tests as well. How would you calculate a p-value here? Of course, a p-value is a probability. So let me put some stuff here. How would you calculate the p-value? Give me the actual expression. Suppose I also do this. Suppose I have a random variable x. It has a chi-squared distribution with 1 degree of freedom. So tell me how you would calculate the p-value here. Remember, all p-value is a measure in terms of probability of how extreme you are, instead of looking at a critical value. Start filling in some of the blanks.
X is greater than 0.5.
Not 0.5.
what's the null hypothesis?
0.4020, your test statistic value. You know, how do you calculate p-values? You know, like for for hypothesis test for mu. Again, it's the probability that a random variable has a t-distribution is greater than, let's say you're doing a two-tailed test. You would have done the absolute value of your observed test statistic value, and you would have multiplied by 2, because it's a two-tailed test. That's all I'm essentially doing here. It's not a two-tailed test, though, so that's why you don't see the 2 there. That's my p-value. How do you think you would do this in R? How would you find that probability? Suggest a function name.
You do p chi-square.
P chi-square,
Or
exactly.
1 minus p chi-square.
Yeah, so let's first look at p chi-square. So p chi sq, so probability chi-square distribution. What you need to do now is give it a quantile to find the corresponding probability. So I could say Q equal 0.4020, my test statistic value, degrees of freedom equal 1. Now what any P then distribution name function gives you in R is the area to the left of it. So the area to the left of 0.40 is 0.47. What we want for a p-value, because it's a right-tailed test, is the area to the right. So then, as what was said, you take 1 minus. That's how you would do it in R. Let's actually do a little plot of this. Let's see. I want to do. Okay, so that's what the chi-square distribution looks like, the chi-square 1, using the curve function. And so what we're doing is, and I'll put a little line on it, vertical line. I'll put a line in there for the test statistic value. I should have done a different color. So there's where my test statistic value is. So if you see where my mouse is, the area to the right of this red line underneath the curve is 0.526. That's my p-value. Notice where my critical value would fall. Let's see, vertical line, 3.84. I'll make that blue. So you can see there's my critical value way out there. Obviously, my test statistic is less than my critical value. The area to the right of this blue line underneath the curve is what? If you could somehow extend that curve out to infinity. 0.05, because that's my alpha. The area to the left, underneath the chi-square distribution there, area to the left of the blue line is 0.95. Are there any questions? Okay, then that concludes then this section 1.1. Let's go into section 1.2. So I really like, I hope others do too, I really like how I laid out my book in terms of we try to start simple. You know, when you have a binary response, the simplest case is what we just got done talking about. Essentially, you know, you have maybe, let's say, a homogeneous population, or a setting where everything else is fixed, and you're just simply looking at the probability of success for that particular situation. So like for field goal kicking, if you, let's say, fix, 40-yard field goal, the weather's exactly the same for every single field goal that you do. Or in my book, you'll see an example dealing with a population prevalence of a disease in a population. If you, let's say that you want to look at the overall prevalence in that kind of a situation, what you're interested in is estimating pi. But there may be other situations then, so now we're going to look at an extension of it, to where you have two groups of individuals. Maybe you have, maybe you're, and you'll see this shortly, maybe you're doing some kind of clinical trial, and you're going to give someone a new drug to see if it cures them, and you're going to also give some other people a placebo. And you want to compare, is the probability of success with this group that got the drug, is it higher? Is it lower? Is it the same as the group that got the placebo? And this is stuff's done all the time to make a judgment of, is this new drug effective or not? Well, let's take a look at some other situations where now you have two groups, or observations fall into two groups. You can also kind of think of this as, suppose you have a covariate, explanatory variable, or independent variable that's simply binary itself, representing the two groups. So here's an example that we're going to be talking about throughout section 1.2. It's about my most favorite basketball player in the history, or my history. One of the best basketball players ever, I think most people will agree, is someone by the name of Larry Bird. I first actually found this data when I was in grad school about 1995, 1996, and I'm still kind of surprised I'm still talking about today, almost 20 years later, and then also probably most of you in this room probably weren't around at the time that the data was collected. So anyway, in basketball, a common thing that's done is you have to shoot free throws. And most commonly, but definitely not always, free throws are shot in pairs. So you do one free throw, and look, is it a success or failure? Did the ball go into the basket? And then you get the ball back, and you shoot another free throw as well, and you look, is it a success or failure? Okay? So only times where you would have to shoot two free throws in succession. We have some data of Larry Bird's free throw attempts from the 1980-81, 81-82 seasons. So for example, on the first attempt, 251 times he made it, and then subsequently made the second attempt. 34 times he made the first, but missed the second. And if you just look at only the first attempt itself, 285 times he made the first attempt, where you don't care about what happens on the second attempt. 5 times we see he missed them both. And then overall, if you were to sum all the stuff that I'm highlighting there, overall the number of pairs of free throws that he shot was 338. Okay? So, what this table here is called, in case you've never heard of this is called a contingency table. It basically shows you the possibilities of all possibilities that could happen. Success or failure on the second attempt, and it just so happens success or failure also on the first attempt, based upon this data example. Now, this is also referred to as a 2x2 contingency table, because there are 2 rows and 2 columns. You might be thinking, wait a second, I see 3 rows and 3 columns. Well, what you should focus on is the stuff that's in yellow, because that's what's summarizing what actually happens pairwise. And the stuff that's on the edges here, or what's often referred to as the margins, are just summaries of what's inside the main part of the table. So it's a 2x2 table. So now, given this data here, and especially for basketball fans out there, what do you think would be a question of interest that you would want to answer with this kind of data?
This is kind of a tangent, but we use Aggressi's book for 218.
Okay.
Some people, and this is the exact, they use this exact table.
Really?
One of the examples when they're talking about determining independence between 2 events.
Well, he got it from me then.
So.
I was using it first because I remember Aggressi's books before, and he did not have that in there. Anyway.
It's from 2012. I think.
Okay. We all borrow from each other. I will borrow from him later on in the semester. So anyway, if you haven't seen this problem before, a question that you might want to ask is, well, is that second attempt, what happens there, is it dependent upon what happens on the first attempt? After all, you might think, again, if you're a basketball fan, you might think that, let's say Larry Bird, he misses that first free throw, and he gets just so down on himself, he psychs himself out, and he's maybe more likely now to miss that second free throw than he would have been if he would have made that first. Because maybe if he made that first, that would give him some confidence, and he would be doing better on that second than if he would have missed. So that's the kind of question that we're going to be interested in. Basically, a test for independence. Or you can think of it another way. Let's say that I want to compare the probability of success on that second attempt for that first row compared to the probability of success on the second attempt for the second row. Compare those two probabilities. Here's another example. I don't know, maybe Aggressy took this also from my stuff. This deals with field goal kicking. We'll be talking about field goal kicking all through the semester because as part of my master's research, I actually did some research in this area. And this data comes from the 1995 season. I actually collected it myself. And what we have here is the success or failure of a field goal with respect to, well, where was the field goal kicked? Was it inside a dome stadium so you wouldn't have to worry about weather conditions? Or was it done outside where you had to worry about stuff like wind? And so, what kind of question would be of interest in this setting? Does the stadium type affect the probability of success? Now, talking about clinical trials again, this is a classic example used probably by a lot of authors, not just me, because it's one of the largest clinical trials ever done. And especially back in the 1950s, this was a big discovery when they found when Jonas Salk came up with the polio vaccine, and then there was another group of people that were also developing their own separate vaccine that actually ended up being better, that I think is what's actually used nowadays. And so what they did in this particular setting, they wanted to know, did this vaccine work? Did it prevent people from getting polio, or at least reduce the probability that someone would get polio? And so look at this. Over 400,000 people were given either the vaccine or the placebo. So that's my two groups. And they observed them over time, and they looked, and they determined, well, did this person come down with polio or not? And so again, with this kind of a setting, you want to determine, well, is the vaccine effective or not? In other words, does the treatment type affect the polio outcome? And then lastly, to put this in a more modern context then, obviously HIV still is a very big problem in our society, and there are a number of groups of researchers that are working on vaccines. Unfortunately, they haven't come up with anything yet. And back in 2009 for the New England Journal of Medicine, there was a paper that talked about the first results of perhaps a vaccine that works. And so this was their actual data that they used to make that kind of judgment. Throughout the medical literature, you're going to see these kinds of 2x2 contingency tables everywhere in order to make a judgment of, well, does a new treatment, does a new drug work or not? And so, I'm not giving you this as homework. I urge you to take a look at exercises 19 through 21 in my book, because there's an interesting story behind this. I won't get into all the details, but I'll just briefly say, so the data was released and the results were released, and they did as you'll see later, a hypothesis test for independence, and the p-value was about 0.04. And they were like, yes, great, we're below 0.05. We have found something. This vaccine looks like it's working. And then about a month later, and I should say that this actually made national news. If we still had paper newspapers, I guess some people still buy paper newspapers. If we still had paper newspapers, it would be, front page. Okay? And then about a month later, they released a slightly different version of the data, where they decided to exclude some people or maybe they decided to include some people. I forget. It was one or the other. And now the p-value, and this was like 9 people. Look at how many people were actually in the sample. After they did that, the p-value became about 0.06 or 0.07. Uh-oh, it's not below 0.05. Well, now maybe our results aren't good. and the reason why I bring that up is that, we're so fixated so often about getting below 0.05 for p-value when we really shouldn't be. What is a p-value? It's basically a statement of how much evidence you have against the null hypothesis. And a statistician who would look at something like that, they would say, yeah, the results didn't really change. You're still essentially having marginal evidence against the null hypothesis. So whether your p-value is 0.049999 or 0.05000001, your conclusion should not be different. You essentially have some evidence, yes, but it's not necessarily strong. Okay? Anyway, I talked about that more than I wanted to. Take a look at the book. It's an interesting discussion of correctly doing statistics and also how media interprets statistics as well. Okay, so section 1.2.1. Basically, we need to take our notation that we had in section 1.1 and extend it now to this setting where now we have two groups of people or items that we're sampling. So instead of having, let's say, y1 through yn as being, oops, go away. Let me just write it someplace else. Instead of having, let's try this again, y1 through yn as Bernoulli outcomes, now we need an extra subscript there to say, is it from group 1 or is it from group 2? And instead of having a sample size of n, I have a sample size of n1 from group 1. I have a sample size of n2 from group 2. Okay? Please note that small little typo in the notes. So then, what's the number of successes that I have? In other words, the what amounts to be the binomial outcome that we have. That's again going to be denoted by W. But I'm going to put a W sub j there to indicate, excuse me, to indicate, well, is j equal 1 for group 1 or is j equal 2 for group 2? This W sub j has a binomial distribution, just like W did before. The number of trials is n sub j. The probability of success on each trial is pi sub j. Again, like what we had before, now with the extra subscript. W1 is going to be independent of W2 in terms of how the sampling's done. One way to think about it, if you're a person, you're either going to be in row 1 or you're going to be in row 2. You're not going to be in both. And as long as you do your sampling correctly, you're going to have the independence done. Now, I guess in a real life setting, that might be somewhat questionable, similar to what we talked about, earlier in section 1.1. Let's say you got 16,000 people here in this study. Let's say you do have one person who's given the vaccine, one person that's given a placebo. Well, maybe they might know each other, and one thing leads to another, I guess, and there goes the independence. In terms of, if one person actually had HIV, it could transmit it to the other person who was in that other group, perhaps. And so, those are some issues, but those are typically minor issues. So then what's the maximum likelihood estimate for pi sub j? Well, as you would expect. Number of successes for group 1 divided by number of trials for group 1. So that's MLE for group 1, similarly for group 2. And there will be times where maybe we want to denote the total number of successes overall across the groups. We'll call that W plus. It's a common way that we use in statistics to say we're summing over things in a subscript, essentially. So we're summing over the rows. So that's where the W plus comes from. Also, we'll have an N plus, meaning the total number of trials. So if we put this notation, I know notation is not necessarily the most exciting thing in the world, but if we put this notation into this 2x2 contingency table, this is simply what we get. So again, if I were to sum up W1 and W2, I get this margin value, W plus. We can also write our notation in terms of the pi's in the contingency table as well. We have pi 1 and pi 2 there. A big focus of this section will be comparing these two values. So what would be one way that you could compare them into, let's say, one overall value? What would you do? Take the difference. So we could look at pi 1 minus pi 2, and that would tell you something. So like with the clinical trial setting, let's say if group 1 was the vaccine, group 2 was the placebo. What you would hope, if the probability of success is, it depends upon how you word it. I think the way I had in the table, that first column was actually, you get the disease. So in that case, you will want pi 1 minus pi 2 to be less than 0. Okay? Also, another way to compare these two is to take one divided by the other. This is what's called the relative risk. Also, another thing that you could do, which will not be necessarily obvious, unless you talked about this in another class, is to do something like this. It's an odds ratio, exactly. So in the numerator, you have what's called the odds of success. And all that is the probability of success divided by the probability of a failure. Do that also for, let's say, row 2. And you divide the 2, you get an odds ratio. So we'll spend a lot of time on that. Odds ratios are used throughout categorical data analysis. So we've talked about just 2 by 2 tables. Larger contingency tables can happen as well. I don't talk about the larger versions until chapter 3. So you could have more than 2 columns, you could have more than 2 rows, but let's just keep it simple with the most, I think the most frequently saw contingency table out there, a 2 by 2. You have to start somewhere. Also, you should think about, well, how could you simulate data under this model structure? How could you simulate, one contingency table of data? What do you think you would do based upon what you learned in section 1.1? What function would help you? You have 2 rows. Both rows correspond to what kind of distribution? Binomial. So what function? R binom. Exactly. So do R binom once, get the row 1 stuff. Do R binom again, get the row 2 stuff. Depending upon what your pi's are, what your n's are, of course. That's how you can simulate a contingency table of data. So let's take a look at the Larry Bird data up close in R. Now, you can actually have R recognize a contingency table structure. Corresponding stuff I do here is in bird.r. The code's not necessarily intuitive the first time that you look at it, but it's really not too bad. And again, like for on a test, maybe I'll have you do some stuff with the contingency table. You can always look back at one of my old programs, like the bird.r program, get the code for the bird contingency table, and then modify the code to fit your own needs for a particular problem on a test or project. So the array function is what you can use in R to enter in a contingency table. If you've worked with arrays in, let's say, maybe a computer science context, you know that arrays allow you to store information in multi-dimensions. Well, here we have 2 dimensions, rows and columns. So the first argument is data. And you simply combine your counts that you have in that table together. And you have to put them in a particular order. Put them in by column. So 251 and 48 is the first column in my bird data. 34 and 5 is my second column. Then for dim, it stands for dimensions. I have a 2 by 2 contingency table. So I just combine together 2 and a 2. Dim names stands for dimension names. What's my names? What would you like to assign for names for my rows? What would you like to assign for names for your columns? And I think this is the least intuitive part of using this function. And you have to create what's called a list. You've all seen lists at least one time before, and that's when in the Intro to R lecture notes, where I used I estimated a simple linear regression model using the LM function, and the results that came back to you from using LM function was a list type object. That doesn't sound familiar? Take a look at the notes again. And so this list basically provides a way for you to put together various bits of information. The first, let's say, bit of information, the first component of this list, that's a better way to say it, is it's going to be called first, because it's going to represent my first free throw attempt. There are two possibilities, made and missed. The second component happens to be called second, because it represents my second free throw attempt. Again, two possibilities, second and miss, or made and miss. And so if I just execute that segment of code, you can see what's given to you. Look at that $sign there. Remember using $signs in the Intro to R lecture notes. So now if I put that in here for my dim names, and I put that into an object called c.table for contingency table, and if I type c.table back, here's my contingency table in R. Any questions about that?
Is first always going to be that first column?
So, excuse me. I think you're referring to this right here.
Yeah.
So that actually is always going to correspond to the row dimension. And then the second part is always going to be the second thing that you put in that list is going to be the column dimension. You could have three-dimensional, you could have four-dimensional contingency tables as well. We'll talk about that briefly in chapter 4. And this array structure gives a nice format to be able to do that. Just worry about 2x2s right now. Now, if I want to extract a certain part of my contingency table, I can refer to it by row and column number. So if I say c.table bracket 1, 1, I get the row 1, column 1 entry. If I say c.table 1, comma, where I don't put any columns there at all, I get column 1 and column 2. In a similar manner, if I did comma 1, I get the first column. If I did sum c.table, I get my total sample size. If I do, there's a function in R called row sums. Notice where the capital letter is with the S. If I do row sum c.table, that gives me 251 plus 34, which is 285. Also gives me 48 plus 5, which is 53. If I want to do the column totals, what function do you think I would use? Call sums. Exactly. So, there's intuitive names here, but, you just have to get used to it. Like, oh yeah, I need that capital letter for the S. Why they did it, I don't know exactly. Okay. How about we find these pi hats? So pi hat 1 and pi hat 2. And also, let's say 1 minus pi hat 1 and 1 minus pi hat 2. So the way I can do that is simply take c.table divided by n1 and n2, which we had found with row sums. Put then an object called pi.hat.table, and there we go. So here's pi hat 1, here's pi hat 2. So, I think a sports fan would hypothesize that the probability of success will be lower on that second attempt if Larry Bird missed the first attempt. That gets into the whole idea of he psychs himself out, let's say. He's so down on himself, it's going to cause him to have a lower probability of success on that second attempt if he missed that first. Based upon this observed data here, what do you think about that hypothesis that I have? What's the observed data saying? Is my hypothesis true or false? False. So he actually does better on that second attempt in terms of a success, probability of success. He actually does better on that second attempt if he actually misses that first one. Again, this is just in the sample. And we know we have variability from one sample to the next. And so a question then that would be of interest is, well, is this difference that we see here really big enough to conclude a generality for all Larry Bird's attempts now or in the past and in the future if he would decide to come out of retirement, is this still going to happen? And so we'll look at it. Let's see here. So now often your data comes to you in a different format than what we just saw there in that contingency table. And instead what often happens is that you get a data format, and I'll just show you the first 6 rows, that looks like this. So we have a column of data, actually 338 observations, that shows what happens on that first attempt. Then we have another column right next to it that shows what happens on the second attempt, 338 observations. So maybe the first time in the 1980-81 season, Larry Bird made the first and made the second. The second time he had a free throw pair, he missed the first, but made the second, and so on. This is often how your data comes to you. Not in the contingency table format that I just showed you, but in this, what I often refer to as the raw format. So what you would like to be able to do is now put it into a 2x2 contingency table. There's a number of ways to do that in R, and we'll talk about 2. There's a function called table. We've already seen the table function before when we were interested in counts for how often did I observe a W equals 0, how often did I observe W equals 1, and so on. What table does here, it now summarizes the counts for both, for essentially both what happens on the first attempt and the second attempt. So all that data 2 is a data frame that contains this raw data that I just showed you. You don't have to worry about how I actually came up with the raw data. You're welcome to see it. I just needed some way to take the stuff that was in the contingency table already and put it into a raw data format. So all that data 2 is a data frame, and one of the variables in that data frame is called first. So if I just highlight all of this, oops, I gotta highlight all of it for all that data. There we go. Okay, you see all the maids and misses. The second attempt is very similar. And so if I use a table function with it, put it into an object called bird.table1, here's my contingency table back. If I want to extract, let's say, the 251 from that table, I would simply say bird.table1 bracket 1 comma 1 in bracket. Another way to summarize the raw data like that is to use the xtabs function. Any thoughts about why it's called xtabs? Anybody heard of crosstabs or cross tabulations before? That's where the name comes from. I don't call it crosstabs. I call it xtabs because it's the letter X there. Anyway, so the first argument is a formula argument, and this is very similar to the formula argument that you saw with the LM function in Intro to R set of notes. And you say formula equal, and then tilde, put in the first variable, put in your second variable, separate them by a plus. The plus basically means in a formula argument, and. Then specify where your data is. I'm going to put that into bird.table2. And there we go. Nicely summarized. Are there any questions? And now that we know how to get a contingency table into R, let's do some stuff with it. So let's go to page 56 of the notes. So the first thing that we're going to do is calculate a confidence interval for the difference of 2 probabilities. In other words, a few minutes ago we talked about how looking at pi 1 minus pi 2 would be of interest. Of course, if that value is equal to 0, that says there's no difference between those 2 probabilities. If pi 1 minus pi 2 was negative, And that says, okay, probability of success for pi 1 is less than it is for pi 2. Let's talk about a confidence interval for it. Now, back in section 1.1, when we were dealing with pi hat, remember what we did. We said that that had an approximate normal distribution to it with a mean of pi and a variance of pi times 1 minus pi divided by n. And we used that information then to come up with our walled interval. Well, the same thing happens here. Now, all I did was I put subscripts on the pi's. So pi hat 1 also has an approximate normal distribution. Pi hat 2 also has an approximate normal distribution. So then, as you might expect, if I were to take then the difference of pi hat 1 minus pi hat 2, of course that's you would think would be a good estimator for pi 1 minus pi 2, which is our real interest. Then as you might expect, that difference also has an approximate normal distribution too for large samples. Intuitively, I think you see why the mean's pi 1 minus pi 2. Well, let's talk about the variance here. Notice all I did was I added the two variances that we saw above. Well, why can I do that? Well, I'm not going to ask you a question necessarily on a test about this, but I think it's good for you to understand how this comes about, especially if you're a statistics major. So if I want to find then the variance of pi hat 1 minus pi hat 2, I can go back to a nice formula that will be taught in a course like Stat 880, Stat 462, Stat 882, a math stat course. And you would see then that this variance then ends up being 1 squared times the variance of pi hat 1 plus negative 1 squared times the variance of pi hat 2 plus 2 times 1 times negative 1 times the covariance of pi hat 1 and pi hat 2. Does that look familiar to some people? Okay. Notice though you don't see the covariance in there in what I'm actually giving you here. Why? Because of independence. The row 1 stuff is independent of the row 2 stuff. That's why that disappears. So that covariance is 0. So then that means then our variance then is just simply the sum of those two the variance of pi hat 1 minus pi hat 2 is just simply the sum of the previous two variances that we have. Now, if I want to find then the estimate of that variance, because of course that variance itself, I would never be able to calculate it because it contains parameters. So if I want to find an estimate for that variance, what do? I put hats on top of the parameters and put in my estimates. I'm really big in tests and projects that you get your hats right. Put hats on the stuff that you mean are statistics or estimators. Don't put hats on stuff that you mean are parameters. Put hats on stuff that you're talking about it's an estimated quantity. This is an estimated variance. I can calculate that. Without that hat there, I can't calculate it because it's dependent upon parameters. Okay, so now that I have this estimated variance then, I can come up with a walled interval for pi 1 minus pi 2. And it's just like what we did last time. Take your estimator, plus or minus value from the standard normal, times the square root of the estimated variance of that estimator. That's my walled interval. And as I say in the notes, do you remember the problems with the walled confidence interval in section 1.1? Hopefully you do. Guess what? They occur here too. So we're not going to use the walled interval at all. Probably a lot of you have seen this walled interval before. Please don't ever use it after you take my class. You will hurt me. This is not a good interval to use. And the reason comes down to, again, the true confidence level. And I think especially after you see some plots similar to what we did before, you'll be like, wow, I can't believe anybody ever taught me to use this particular interval before. Because you'll see some plots where you never get up to 95%, even though you state 95%. You never do. And that's really sad to see something like that happen. Okay, time is 3:45, so we are done here. Are there any questions? Okay, that's it for today.